Welcome back to our last lecture for Chapter 4. For this lecture, we are going to be looking specifically at binomial distributions. A binomial distribution is a type of discrete probability distribution where the outcomes take on exactly two values. In fact, in our previous video, we have two probability distributions, one of which is, well, our roll of the dice, that's one of ours. And this other one, this outcome one here, this is a binomial probability distribution. And you have two outcomes, either heads or tails. So flipping a coin, making a basket, if you shoot a basketball, passing a class, supporting a political candidate with a yes or no. These all have exactly two outcomes. And in general, we call these outcomes success and failure. Success is not necessarily a good thing. It is just the observation or just the outcome that we are looking for. And likewise, failure is not necessarily a bad thing. So here's an example where success is good, passing a class. Success means you pass. That's a good thing. An example where success is bad, screening for a disease. A positive result, which is success, means you have the disease. That is bad. So keep in mind when I say success and failure, I'm not talking about good and bad. I'm just talking about the outcome we are looking for versus the other outcome. A binomial probability distribution or a binomial distribution. Let me start over. Binomial distributions are used a lot because so much in life is yes, no, true, false, success, failure. In fact, just about every statistical question could be posed as a yes, no question. And so this is a very important distribution to investigate. There are a number of questions we can ask about probability distributions. So I'm going to list those questions and I'll give you an example. So the very first question is questions for binomial distributions. The very first one is just, what is the probability of success? And what's the probability of failure, which is just going to be the other side of that coin. Another question is, in a sample of size n, right, where n could be 100 or n could be 30, how many successes would we expect? That is an expected value. And then we could also ask, in a sample of size n, how likely would it be that we have no successes or all successes or any specific number of successes? And another question we might ask is, in a sample of size n, I hope you're seeing a trend here. We often start with a sample of size n. How likely would it be that we have, let's say, no more than 10 successes? And let's give some numbers. In a size n equals 30, how likely would it be that we have no more than 10 successes? how likely are we to have at least 22 successes? And then the last question is, if someone claims that the probability of success is high, how likely is it that we would observe very few successes? And does this mean that their claim is wrong? So I'm going to talk through each of these in turn, using an example. Stephen Curry, if you don't know who Stephen Curry is the greatest shooter of all time in the NBA. He regularly makes really deep three-pointers in the heat of the game. So let's suppose that Curry takes 50 three-pointers and makes 20, let's say 34 of them. Let's ask our first question. What is the probability or the proportion? What proportion of the three-pointers did Curry make? That's a pretty easy question. That's just 50 divided by 34. Nope, I'm sorry, I got it wrong. 34 makes out of 50 tries, which is 0.68. This is our best guess as to Curry's general likelihood of making a three-pointer. We collected a pretty big sample, 50, and he made 34. So in answer to our question, what is the probability of success is probably 0.68. All right. How about what if Curry took 23 pointers? How many would we expect Curry to make? Well, to answer that question, we would take we could think about this as a table using our binomial distribution to fill out a table. But in general, we can do this a little bit more quickly. We let n equal 20, the number of trials. Yep. Let p equal 0.068, the probability of making any given three-pointer. Then the expected number of successes, this is an expected value, is n times p. 20 times 0.68. 13.6. The interpretation is, while Curry would never make exactly 13.6 out of 20 three-pointers, because you can't make a fractional three-pointer. If Curry took 20 shots a bunch of different times, and you average the number of makes each time he took the 20 shots, you would expect that the average is close to 13.6. And I'll go ahead and do the table real quick, just so you can see how that links up with the discrete probability distribution. So this is the outcome, success, failure. We're going to give it a value. And in a binomial distribution, we usually give the success a value of 1 and a failure a value of 0. The probability, well, our data indicates that the probability of a success is 0.68 and the probability of a failure is 0.32. So value times the probability is 1 times 0.68 plus 0 times 0.32. So the expected value of a single shot is 0.68. So the expected value of 20 shots is 0.68 plus 0.68 plus 0.68. And we do that 20 times. Which is 13.6. We can also ask about the standard deviation, which is kind of strange to think about. He's either going to make it or he's going to miss it. But we can also ask about the standard deviation. So I'm just going to give you that information now. The standard deviation if Curry takes 20 shots. So this is a binomial distribution. And I'm just going to give you the formula. It's the square root of the probability of making it times the probability of missing it, which is 1 minus p. If 0.68 is p, 1 minus 0.68, 1 minus p is 0.32. And then you take that and you divide it by the number of trials. And this formula is in your book. All right, so that was, let me change this. Okay. That's proportion of successes, proportion of probability of success, sample size of sample size of 20, how many successes would we expect? All right, now we get into the deeper statistical questions. In a sample size n, how likely would it be that we have no successes? So if Curry took 20 shots, how likely would it be that he makes 0 shots? You can probably answer pretty unlikely. Right? That's a good first approximation. If he, on average, makes 68% of his shots, he's probably not going to miss all of them out of 20. But we can get this exact probability using a little bit of math or mathematical notation. So the probability of making 0 shots out of 20 if the likelihood of making any given shot is 0.68. We do the probability that x equals 0 out of 20 given that little p equals 0.68. That's the notation that I like to use. Well, let's assume that Curry doesn't isn't psychologically affected by missing his shots, so that any given shot has the same probability of going in. If he misses the first five, that's not going to affect the probability that he makes the second shot or the sixth shot. So if he's going to make none of them, he must miss the first one, and he has a 32% chance of missing that one, 0.32 probability. And then he misses the next one, which is also 0.32. And he misses the next one, which is also a 0.32. And we multiply 0.32 every single time. And so what we get is 0.32 raised to the power 20. Oh, that's a small number. E to the minus 10 means 1.267 times 10 to the negative 10. Or point, like move that decimal places over 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 6, 7. That's a tiny probability. Which hopefully makes sense. Stephen Curry is a great shooter. He's not going to miss all of them. How about the probability that it makes all the shots? Well, let's find out. So the probability that X equals 20 out of 20, given that P is 0.68, that's 0.68 times 0.68 times 0.68, which is 0.68 to the 20th, which is also a tiny number. Let's see if I can get an actual decimal approximation of that. But not as small. Right, there's still a tiny chance. That's like 4 out of 10,000. So the interpretation is if Curry took 20 shots, he would have to do this about 10,000 times in order to make all 20 shots at least 4 times. Right, that's not very likely. All right. The deeper question is, how about any specific number of successes? So we're up to question 5. Let's see. Curry took 20 shots. How likely is it that he makes exactly 9 of those shots, given that his individual success probability is 0.68? So to do this, I'm going to introduce the notation. I've deliberately held back on these other notations until now, just to talk through it. But now I want to give you like the notation that statistics use for these types of questions. So we start with N is the number of trials, in this case, 20 shots. K is the number of successes, in this case, 9 successes. P is the probability of an individual success, 0.68. X is the random variable that just shows up. Let me put here 1 minus P is the probability of an individual failure, which in this case is 0.32. So X is a random variable that just shows up, and then capital P is the probability of K successes out of N trials given little p. So in this case, probability that X equals 9 out of 20 given little p equals 0.68. All right, this is going to be hopefully one of the few times I'm going to use equation notation as opposed to just the type of typing that you've seen so far. The formula for this is called the binomial probability formula. The probability that X equals 9 out of 20, given that P equals 0.68 is I'm going to pause so I know how to write this text. Okay, figured it out. All right, so the formula looks like N choose K times little p to the N times 1 minus little p to the N minus K. That's what the formula looks like. You read this as N choose K times P to the N times 1 minus P to the N minus K. N choose K times P to the N times 1 minus P to the N minus K. We can go one more step and use the fraction form of this N choose K, which is N factorial over K factorial times N minus K factorial times P to the N times 1 minus P to the N minus K. If this notation looks completely foreign to you, that is okay with me. That hopefully it can be okay with you. Because we're going to use R whenever we have to calculate this. But I'm still going to go one more step just for those of you who are interested. What does factorial mean? Well, factorial means you take n factorial is n times n minus 1 times n minus 2 all the way down to 3 times 2 times 1. And on the bottom, you have a k factorial. So that's k times k minus 1 all the way down to 3 times 2 times 1. And then you also have the n minus k, so that's going to be n minus k times n minus k minus 1 all the way down to, I have to split this into two. All right. I'm going to have to split that into two different, this is frustrating. All the way down to 3 times 2 times 1, and then times p to the n times 1 minus p to the n minus 1. All right, that's the formula. Is it nasty? Yes, it is. Does R care? No, it does not. R can do this formula exceedingly quickly. I'm going to do it once by hand with these numbers here. You don't ever have to do this by hand. I encourage you to use R to do this every single time. But here we go. So um, I'm going to change that right now because I used n's out of n given p. There we go. Okay, here we go. So with n equal 20, k equal 9, little p equals 0.68, probability that x equals 9 out of 20 given little p equals 0.68 equals 20 choose 9 times 0.68 to the, ooh, I got that wrong. That's a K, not an N. My apologies. All right, if you've been listening without looking, I'll read it one more time. N choose K times P to the K times 1 minus P to the N minus K. So we get the 0.68 and we raise that to the 9 successes. And then we do the 0.32 and we raise that to the 20 minus 9 successes, failures. So that's going to be 20 factorial over 9 factorial times, well, 20 minus 9 is 11, so 11 factorial times 0.68 to the 9th times 0.32 to the 11th. And I'm going to hop over to R and do the rest of this in R. So brute forcing a binomial distribution probability. We have n equals 20, k equals 9, little p equals 0.68. So we want n factorial. I think it's this. Nope. Nope. There it is. That's a big number. E plus 18 means 2.4 times 10 to the 18th. That's probably too big to work with. But what we can do is we can do factorial of n divided by factorial of k times factorial of n minus k. That's not going to be so bad. Oops. Misspelling. There we go. That's not too bad. 167,960. And now we do p to the 9th and 1 minus p to the 11th, p to the 9th, and 1 minus p to the 11th. Pretty small. And then we multiply those all together. I'm going to go that times that times that. And what do we get? We get 0.188. Okay, let me drop this in here. Using R to brute force the calculation. So the interpretation is if Steph Curry takes 20 3-pointers, the probability that he makes exactly 9 3-pointers is 0.188. 0.0, yeah, 0. Did I get that right? I think I got it wrong. There's an extra 0 in there. 0.0188. So if he took the 23 pointers a bunch of different times, about, let's see, 1.8% of the time, he would make 9 of them. That's the interpretation. But we don't want to brute force this. So we're going to use R to quickly calculate this probability. And this is how I want you to do it all the time. It's a very simple code. It's simply P binom. Okay, sorry, using R to calculate the probability of making 9 out of 20 given little p equals 0.68. It's just P binom. It might be D binom. It's D binom. 9 successes, 20 attempts, 0.68 probability. There it is, exact same number. So that is how I want you to always calculate the probability of an exact number of successes out of a certain number of trials. And your MyOpenMath homework has some of those questions on there. All right, this video is going a little long, but we have a couple more things to cover. So we talked about the probability of making a specific number of successes. What about if we have 10 or fewer, or 22 or more? So not a specific number, but a range of probabilities, or a range of number of successes. So what is the probability that Steph Curry makes 9 or fewer shots out of 20, i.e., he makes 9 or 8 or 7 or 0. Well, that probability, we can think about it in a pretty straightforward way. The probability that x is less than or equal to 9 out of 20 given p equals 0.68. That's just the probability that he makes 9 out of 20 given p equals 0.68 plus the probability that he makes 8 plus the probability that he makes 7 all the way down to the probability that he makes 0. And we just add up all those different probabilities. So you could do that in R by doing d binom of 9 plus d binom of 8 plus all the way down to d binom of 0. That would work, but R actually has code. Using R code to quickly calculate this probability. And the code is very simple. The code is just, instead of dbinom, we're going to do 9 or less out of 20. We use pbinom. And we want, all right, we want 9 or fewer successes out of 20, where the probability is 0.68. Lower tail equals true means we're doing less than, and we run it, and there's our probability, 2.79%. So the interpretation, oops. So the interpretation is if Curry took 20 shots a number of times, then you would expect him to make 9 or fewer about 2.8% of the time. And we can double check if we wanted to, but I'm too lazy, by adding up all of these different dbinoms, but that would take a lot of work, and I don't want to do that right now. Okay, what about the probability of making, let's see, 17, 18, 19, or 20 shots out of 20? We have to be a little bit careful because pbinom defaults to the probability of making less than or equal to. So as long as we keep that in mind, we can use R to quickly figure out this probability as well. So using R to calculate probability at X is 17 or more out of 20, where P is 0.68. That's equal to 1 minus the probability that X equals 16 or less out of 20. P equals 0.68. So that's what we're going to do. We're going to do 1 minus the probability of making 16 or fewer out of 20, given that the probability of a single success is 0.68. There we go. It's 7.65. Uh, 0.0765. So the interpretation is if Curry took 20 shots a number of times, then you would expect him to make 17 or more about 7.65% of the time. All right, last question. If someone claims the probability of success is high, how likely is it that we would observe very few successes? And does that mean their claim is wrong? So this is 7. So suppose I claim that I make 50% of my 3-pointers. You are maybe a bit doubtful because I am a math teacher, not a basketball player. But who knows? Maybe that's a hidden talent. So you challenge me to take 20 shots. I make 4 of them. Do you think my 50% claim is accurate? Or do you have statistical evidence that it is not accurate? And this goes back to the Wizard of Oz question. So my claim that I make 50% of my three-pointers is Kansas. When I take 20 and make 4, those might be ruby slippers. If they are ruby slippers, I'm actually in Oz, where my probability of making a three-pointer is definitely not 50%. So the statistical question is making 4 out of 20 so unlikely if my true form is 50% that my claim that I make 50% is wrong? And this is where statistics can get you into verbal knots, and why I want you to think through, and maybe think through the Kansas versus Oz question as opposed to the numbers every time. But the way I would phrase this for statistical purposes is it so unlikely that I would make 4 or fewer shots out of 20 if my true average, or if my true success rate were 50%, that the fact that I made 4 out of 20 means my true success rate is not 50%. So we can ask this question using the probability calculation. What is the probability that I make 4 out of x equals 4 out of 20, given that my success rate is 0.5? And so we'll hop over to R to ask that question. Using R to test the claim that I make 50% of my three-pointers if I made 4 out of 20 in a trial. So N is 20, K is 4, P is supposedly 0.5, and I want the probability that X is 4 or fewer out of 20, given P is supposedly 0.5. So that's P binom with 4, 20, and 0.5. And that probability is 0.0059%. Answer is 0.00, sorry, not percent, 0.0059. Or 0.59%. The interpretation: if my true success rate is 50%, then the probability of making 4 or fewer out of 20 is only 0.59%, i.e., would happen only about 1 time out of every 200 times taking 20 shots. That seems like ruby slippers to me. The probability of such a low success rate is very small. So it is, how about of such a low success quantity is very small, so it's more likely that the claim success rate is not accurate. Probably my actual success rate is not 50%, but more like, I don't know, 20%. So that's how we can use our probability, or sorry, our binomial distribution to ask these questions about claims. I claim I make 50% of my three-pointers. I take 20 shots and make 4 of them. You calculate that mathematically, that's super unlikely, but I did make 4 of them. So what's more likely? That I had an absolutely terrible day, or that in fact, I'm not that good at taking three-pointers? I don't think we're in Kansas anymore. All right, this concludes the video. I'll be back with videos for chapter 5 in the coming days. Thank you very much.